Okay, now let's get on to this session. So I welcome you all for the week 3 live interactive session for the course Polymers Concepts, Properties, Uses and Sustainability. I think we have Lakshman as a new student this week, right? Can you just give a brief of yourself, Lakshman? What are you doing? Where are you from?
Hi ma'am, I am Lakshman from IIT Hyderabad.
Okay,
So I'm doing a postdoc here. I just
oh,
joined recently.
okay.
So I'm from here itself, Andhra.
Acha, okay, 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 okay. So what was your PhD work on and where did you do it?
My work is on amorphous materials. I did it from Manipal University, Karnataka.
Oh, okay. That's nice. So, what is the purpose of joining this polymer course?
I have worked extensively on small molecules. Like I'm from a pharma background, not from engineering.
Okay.
My background is from B.Pharm, M.Pharm, and PhD. So I worked on drugs and molecules. So I want to learn about polymers and design carriers for drug delivery. So those kind of things.
Okay, okay, okay. I welcome you to the session. Now, let's get officially get into the session. Uh, okay, I'll just share my screen. Hope you're all able to see my screen. Are you able to hear me and see my screen?
Yes, yes,
Okay,
ma'am.
okay, fine. I welcome you all for the live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. The course instructor for this course is Professor Abhijit Deshpande from IIT Madras. And the live session is handled by myself, Kritika. I'm a PMRF research scholar at IIT Madras. Okay. So I request you all to actively participate in the session. It's a live interactive session. Okay. So we'll be having a brief recap of lectures of week 3 followed by some practice assignment questions. So I request you to actively participate, try answering whether, don't hesitate whether it will be right or wrong, whatever be it, just try to answer. We all are going to learn at the end of the day. Okay. And I request you to have some notebook, pen and calculator if possible, because we'll be doing some numericals. Okay. uh, yeah. And so and also I request you all to please go through the lectures before the session so that in case you have any doubts, you can get it clarified. Also, you can ask your doubts through the forum, okay, where the course instructor or myself, under the guidance of course instructor, will be answering your queries. uh, and also, going through the lectures before this live session, it will help you to participate much more actively, because you will be going, knowing the concept that was discussed in the week's lectures, and that will make you to actively, much more actively participate. Okay. Now let's get on to the session. So did any of you go through the week 3 lectures? I need some.
Yes, ma'am. For me, one more video is left, the last one.
Okay, okay, so you're yet to see the glass transition video. Okay,
Yeah, just started actually.
okay, okay, fine. Okay, so that's good. So please go through the lectures. Okay. Because a lot of effort has been put in by the professor. Okay, you could see how beautifully, each lecture is designed. uh, the concepts, you know everything. So please go through the lectures. Okay. Yeah. uh, uh, you were able to solve the assignment 1 and 2.
Yes, ma'am.
Okay, okay. So you saw the solutions. So were you able to get the similar answers, or you found a lot of difficulty in answering?
Yeah, some are difficult, some are okay.
So you went through the
Found
solutions that,
numericals difficult.
oh,
Numericals, I found it difficult.
okay, it will be little challenging. Okay, it will not be just directly direct questions. You will have to put in little bit of an effort. Okay, that is what learning is all about. You have to put in little bit of effort, and also you have to try to go through the textbook which is mentioned by the course instructor, and also the references, so that you will get much more idea of the questions asked, and also for a learning point of view. Okay, nevertheless, if you have any doubts, you're free to ask either in the live interactive session or through the forum. Okay, and your queries will be answered. Okay, and someone, I think in the previous week, I think the week one, they had informed that the biopolymers lecture 4, it was incomplete. Now the complete lecture has been uploaded. You can view the lecture. Okay, uh, I just wanted to update that. And
Yeah.
fine. When you went through the solutions, were you clear?
Ah, yes.
Uh,
After viewing the solution, it was clear.
Clear. Okay, very good. Nice. Now let's go through the recap of lectures of week 3. So this week 3 lectures were on molecular arrangements and states of polymers. Okay. So lecture 16, it was on structure in biopolymers. So biopolymers, obviously, this brings in the sustainability aspects. Here, molecular structure of biopolymers were discussed, right? Different structural levels were discussed, right? What were the different structural levels? Do you remember?
Ah, yes, ma'am. Primary, secondary, tertiary, and quaternary.
Yes, yes, yes. Okay, that's good. So, and then there was the discussion on polynucleic acid, where DNA as a molecule for engineering was discussed. And next, under proteins, cousin and its hierarchical structure was discussed. Right? Where do you find this cousin?
The milk
Yes, yes, correct. Yeah. And what application was discussed in the lecture? Do you remember?
transformers. It will be used in transformers as
Uh,
a fluctuations
it, it is used as a adhesive. Okay, in
headers.
transformer application. And finally, polysaccharides were discussed. Here, the lower role of polysaccharides. And then there was a discussion on pectin. Uh, do any of you know where is pectin used in your day-to-day life products, commercial products?
In the
Huh?
food,
Yeah, in food. Yes, correct. Uh, in which food specifically? A very common food. It's used in jams and jellies. So
uh,
every one of you would have had jams and jellies at some point of time, right?
yeah, yeah.
Yeah, so it is extensively used in jams and jellies. Okay. But nevertheless, it has wide range of applications as well. Okay. Yeah. Now let's go on to what was discussed in lecture 17. So lecture 17 was on amorphous and crystalline states. Okay. So this was on concepts. Okay, based on amorphous and crystalline states. So how do we go from a liquid to solid state? And what are the important semi-crystalline polymers were discussed? So features of crystals in atomic crystal systems and all were discussed. Okay, some idea on this unit cells, and then how does crystallization in atomic system takes place were discussed. And then macromolecules in crystalline form was introduced. And yeah, how crystals are observed in natural polymers like protein was discussed. And finally, polycrystalline state of polymers and spherulites were discussed in this lecture. Correct? Correct.
Yes, ma'am.
And yeah, now
Yes, ma'am.
let's proceed further. Again, lecture 18 was on amorphous and crystalline states. This was again a concept-based lecture. So, what is the thermodynamic description of crystallization and melting was discussed. There was a discussion on first order transition, and then crystallization of polymers. What are the complexities involved in crystallization of polymers? and the inherent kinetic factors in polymer crystallization, like the rate of crystallization and what happens when there is a mixture of polymers, right? So these aspects were discussed. Lecture 19 was on orientation. It is a uses based lecture. So orientation and how it is quantitatively measured. So there was a discussion on molecules, orientation in molecules, crystallites, domains in case of polymer blends, fibers and fillers orientation in case of polymer composites, and how is this orientation quantified, and what are the applications where this orientation uh, is done, and how important it is. uh, okay, so these aspects were discussed, and what are the orientations that are taking place during processing, different processing, right? So these aspects were discussed. Lecture 20 was on interactions. So it was again a concept based lecture. So interaction of polymers at molecular levels, what are different non-covalent interactions present, and the hard sphere and square well models and Lennard-Jones potential was discussed, right? And uh, the next one was on interaction in polymers. It was a discussion on the coarse grain level approach and empirical approach. Lecture 21 was on kinetics of crystallization. Right, because in crystallization, in case of macromolecules, the kinetics of crystallization also plays a important role in what is it crystallization, the crystallinity present in the final polymer sample, correct? So so this was a property based lecture. So glass transition and melting were introduced, and polymer crystallization and how does the structure and growth of polymer crystals happens, and the crystallization as a function of temperature, lamellar thickness is a function of temperature, and two crystallization models, right? One was Avrami model and another one was Ozawa model. So these two models were discussed, correct? And the final lecture of the week was on glass transition, glass transition. It is a property based lecture. So first, there was an introduction on amorphous state of polymers, and then properties in glassy states, and uh, the glass transition temperature that depends on history. So a brief of all these aspects were given. And then what happens when there is a glass to rubber transition, and there was a discussion on dialectrometry and importance of glass transition, because this glass transition plays a very important role in understanding polymers and polymer behavior and their applications. So those all aspects were all given an idea. Fine. Are you all clear? Hello, both of you, are you there?
Yes, ma'am.
Okay. So I just brushed up what was all discussed in the week's lecture. Now let's go on to the week 3 practice assignment. Okay. First, polynucleic acid, proteins, and polysaccharides are biomacromolecule families. So the primary structure of biomacromolecules can be linear or branched. Right? Pick the correct pairing from the following. So now you have to pick the pairing. So for example, whether in case of polynucleic acid is given the number 1, proteins 2, polysaccharides 3. Now you have to match what kind of a primary structure do these have, whether it is going to be linear or branched or a combination of both. Okay, so is it 1 linear, 2 linear or branched, 3 linear, or is it 1 linear, 2 linear, and 3 linear or branched, or is it 1 linear or branched, 2 linear or branched, and 3 is linear, and 1 is linear or branched, 2 is linear, 3 is linear. So which one is correct?
I would go with option B. Linear, linear, and linear or branch.
Okay. So you're saying polynucleic acid, they have a primary structure which is linear, proteins which are having primary structure linear, and then Polysaccharides have linear or branched. Okay, you're saying this as an option. Okay, so what about the others two person? What about Lakshman?
I think it might be D. I'm thinking D.
Okay, you're saying polynucleic acid is linear or branched. Proteins and polysaccharides are linear. Okay, so I have got two different answers. So let's see. Okay, why do you say option D?
Polysaccharides, I thought it is linear first thing.
Okay, okay,
Proteins, they might be linear or branched actually. But polynucleic acid DNA is again linear or branched.
okay. So you're giving me okay. Okay, let's see what is the answer. The actual answer is polynucleic acid and proteins are linear. Okay, whereas polysaccharides, they are linear or branched. So these polysaccharides, they have a lot of branching, especially in the branches you have a lot of sugar units. Okay, in case of that is why, in case of structural determination uh, of polynucleic acid and proteins, it is a sequence of nucleic acid or sequence of the amino acids which play a vital role in the structure. Whereas in case of polysaccharides, all your stereo, regioisomerism, the linear and branching, every lot of aspects come into picture. Okay.
Yes, ma'am.
Okay. Okay. Now the next question. So this is a GATE 2021 question. Okay. When the rate of cooling is increased due to solidification process, the glass transition temperature of a polymer, whether it decreases or it increases or it stays unaltered or it shows a non-monotonic dependence.
I would tell it increases.
You're saying it increases. So if the rate of cooling is increased, so the glass transition temperature will be higher. Okay. So uh
Decreases.
okay, there are two options given. Okay, let's see what is the answer. It actually increases. So when the rate of cooling is, increased, the glass transition temperature, the temperature at which the arresting takes place will be increased. Okay, so it is actually increases if the rate of cooling is, increased. Fine.
Ma'am, can you explain it again? I didn't understand.
See, if there is a faster rate of cooling, no, you're not giving a
Yes,
lot
ma'am.
of time for the material to really, feel the changes happening to it, and it starts getting arrested. Okay, the movement starts getting arrested. See, glass transition basically decides how whether there's a segmental flexibility or not, because in a macromolecule, polymer is a long chain. Okay, there are a lot of segments, right? The polymer
Yes,
chain
ma'am.
has segments. So this segmental arrest, okay, if you're trying to cool it at a very higher pace, it happens much more faster. Okay, it stops, becoming it stops its movement, or it starts getting frozen in its state at a much higher temperature. Okay.
But
Okay, ma'am.
glass
I understood.
transition temperature is, I think, an inherent property. No?
See, it is not a single temperature. You will have it in a range only.
Oh,
Okay. Yeah.
yes.
Yeah. Yeah, we'll discuss this further. Okay. So the next is a problem. Okay, numerical. So just requesting you to have your notebook and calculator. Okay. There are two different uh, PTFE polymer specimens of the following density and percentage crystallinity. For specimen 1, the density is 2.144 gram per centimeter cube, and the percentage crystallinity is 50. For specimen 2, the density is 2.215 gram per centimeter cube and percentage crystallinity is 75. Okay. Now assuming the polymer is pure and defect free, the density of 100% amorphous PTFE specimen will be what? So what have they given in the question? So this is again a GATE 2021 question. Okay. So what have they given in this question? So they have given two different PTFE polymer specimens, and for each specimen they have given the density and the percentage of crystallinity. Okay. Now they have asked what will be the density if the PTFE specimen is going to be 100% amorphous. Okay. Now, so how do we start this problem? Any idea? Any thought process?
Ma'am, no idea.
Okay, now let's see how the solution is. Lakshman, you want to answer something?
No, no, ma'am.
Okay. Let's proceed with the answer. So let's start. So as we discussed, they have given the density of specimen 1 and percentage crystallinity. So now this percentage crystallinity is 50% in polymer 1. Specimen 1. So that means the volume fraction of crystallinity is 0.5. Similarly, for specimen 2, they've given the density and the volume fraction is 0.75. The crystallinity, percentage crystallinity they have given, and the volume fraction from that is 0.75. Okay. Now, there is a relation between volume fraction, okay, of a polymer specimen and the density of the overall specimen, density of amorphous phase, and the density of the crystalline phase. So that is what is given in this relation. So phi C is equal to rho minus rho A by rho C minus rho A, where rho is the overall density of a particular specimen, rho A is the density of the amorphous phase, and rho C is the density of the crystalline phase. Now we just have to rearrange this formula, because what we have to find out is what will be the density of the amorphous phase when the specimen is 100% amorphous. Nothing but rho A we have to find out. So we have to just rearrange, right, the equation. So rho C minus rho A is equal to phi C into rho minus rho A. Now for specimen 1, we have the overall density, we have phi C. Similarly for specimen 2, we have rho and we also have phi C. Okay. And another information we have is both are PTFE polymer, right? So rho C in case 1 and case 2. Similarly, rho A in case 1 and case 2 will be same, correct? It will not be different. The overall density might be varying because of the percentage of crystallinity, but the crystalline phase density and the amorphous phase density is not going to change with the specimen, correct? So we just have to incorporate whatever data we have. So we have two equations and two unknowns, right? Rho C also we do not know, rho A also we do not know. So we just have to solve this equation, correct? Correct.
Yes, ma'am.
Yeah.
Yes, ma'am.
Now someone can solve this equation and say what is the value of rho C and rho A.
Ma'am, the value we need is of rho A, right?
Yeah, rho A is the answer we have to find out. So subsequently we can find out what is rho C also.
Ma'am, I got the answer as 2.357.
Okay. Uh, what about Lakshman?
2.63.
So each of you are saying what is the amorphous phase density, right? Or you're saying crystalline phase density? Because both of you are saying two different values. So I just want to know who is saying which value.
Amorphous, I'm telling.
Amorphous.
Okay. Okay, let's see what is the answer. So assuming rho A and rho C are constant for both the specimen and equating 1 and 2. Okay. We get, so we are just equating because the left hand side of both the equations are same. So we are just going to equate the right hand side. So that you will end up with what is rho A. So the rho A value is 2.002 gram per centimeter cube. Okay, this is the density of a 100% amorphous PTFE. So maybe some calculation error might have happened. Don't worry about that. End of the day, you should know what is the concept. Okay.
Yes.
Yep.
Ma'am.
Yep. Now let's go to the next question. The enthalpy of fusion for a polymer is found to decrease from 135.6 joule per gram to 120 joule per gram after 5 years of use. Okay. If the enthalpy of fusion of the same polymer with 100% crystallinity is 290 joule per gram, then the loss in crystallinity after 5 years is dash. So this is again a GATE question, GATE 2022 question. So what have they given? They have given enthalpy of fusion of a polymer at some point of time and after 5 years, and it's found that the enthalpy decreased from 135.6 to 120. Okay, and then they have given enthalpy of fusion of the same polymer with 100% crystallinity, which is 290 joule per gram. So that means this value 135 shows that the polymer is not 100% crystalline, so it does have a amorphous phase. Okay, and now we have to find out how much there is a loss in crystallinity after 5 years. So how to proceed this? Any idea?
Ma'am, we will calculate the percentage crystallinity for each case for the firm and we'll find the difference.
Okay. What about you, Lakshman? What are you saying?
Yeah, no idea, ma'am, about this.
Okay. 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 But how do you find the percentage crystallinity in each case?
I have no idea, ma'am.
Okay. Now let's see how the solution goes about. So they've given heat of fusion of polymer crystal, that is 290 joule per gram. Polymer crystal nothing but 100% crystalline polymer. Okay. They have also given heat of fusion of polymer at some time point t, which is 135.6 joule per gram, and then heat of fusion at some time t2, which is after 5 years of use, which is 120 joule per gram. Okay. Now there's a relation between your heat of fusion at any point of time and heat of fusion of polymer crystal and the crystalline fraction, okay, which is Xc. So from this, as you said, we can find out what is the crystalline fraction. So Xc is delta HF by delta HFC. Okay. Now change in degree of crystallinity or loss in crystallinity after 5 years. So how do we find? So it will be nothing but Xc is nothing but delta HF1 minus delta HF2 by delta HFC. Okay, that will give you what is the change in crystallinity. Okay, it is nothing but crystallinity at some time point minus crystallinity at some other time point, so which is given by this delta HF by delta HFC. So you will find out that this is a difference between the delta HF1 minus delta HF2 divided by delta HFC. So you have what is the crystallinity? No, decrease in crystallinity after 5 years, or loss in crystallinity. Okay, change in, so it is nothing but 0.05379, which is nothing but about, there is a 5.4% loss in crystallinity from the initial crystallinity. Okay, there is a 5%, nearly 5.4% decrease in crystallinity from the initial crystallinity after 5 years. Okay, so from this again, what was the initial crystallinity you can find out, because Xc is nothing but your delta HF by delta HFC. So you have what is delta HF at time point 1, which is 135, and delta HFC, which is 290. So you can find out Xc is 0.46, which is nothing but 46.76%. And after 5 years, it is, the heat of fusion reduces to 120, and heat of fusion of polymer crystal is 290. So dividing that, you will get the crystallinity is 41.38. So if we find out the difference this way, you again end up with the loss in crystallinity as 5.4%. Okay, you both of you got it?
Yes, ma'am.
Yes, ma'am.
Got it.
Oh, the next question. Quenching from melt results in, does it result in crystalline solid, amorphous solid, semi-crystalline solid, or none of the above?
Semi-crystalline solid.
Amorphous solid.
Okay. What does quenching means?
We have to
Sudden
cool,
cooling.
sudden cooling.
Okay. So what if we suddenly cool the material? Will it have ample time to arrange itself, or it is under a shock that it just gets frozen and there is no proper, kind of a
It's a
arrangement?
disorder system will form.
Yes. Yes. So Lakshman is right. You will end up with amorphous solid. So quenching, as you said, it's a rapid cooling. Okay. Sudden cooling. Okay. So when there is a sudden cooling, what happens? Your material doesn't have, ample amount of time to settle itself and arrange itself in some ordered fashion. So what you end up with is a completely disordered fashion, which is nothing but an amorphous solid. Okay. Paul, you got it?
Yes, ma'am. Got it.
Okay. Yes. Good. Now next. Two miscible polymers A and B are blended in weight ratio of 30:70. If the glass transition temperature Tg of polymer A is -50 and that of polymer B is 100, then the glass transition temperature of the blend is, what will be the glass transition temperature of the blend? So this is again a GATE 2012 question. So what are the things that are given? It's given that there are two miscible polymers, okay, A and B, and they are blended in a particular weight ratio. They've also given what is the glass transition temperature of pure A and what is the glass transition temperature of pure B. Okay, now they are asking what will be the glass transition temperature of the blend. So how do you find it?
Gordon-Taylor equation.
Okay, okay, okay. Before getting into the equation, now let's see logically uh, what will be the probable glass transition, whether it will be,
It will be in the between of those two. If it is ideally mixing and miscible with.
okay, they have given miscible polymers. Okay, so they have given miscible polymers, so there is no doubt about it. So it will be between. So now tell me whether it will be closer to -50 or whether it will be closer to 100.
It will be plus 50, not closer to 100, or it will be towards positive side, maybe 50.
Okay, No, I'm asking whether it will be the blend will have a glass transition closer to that of a polymer A, or whether it will have glass transition temperature closer to that of polymer B.
Polymer B.
Okay, why do you say it will be closer to polymer B glass transition?
The composition is high of B.
Yes, you are right. Okay, now let's see how to solve this. Okay, so as we discussed, Tg of polymer A is -50, polymer B is 100, weight ratio is 30:70. Okay, you have the relation called Fleury-Fox equation. Okay, this gives what will be the glass transition temperature of a blend. So this equation is given by 1 by Tg is equal to weight fraction of polymer 1 by glass transition of polymer 1 plus weight fraction of polymer 2 by glass transition of polymer 2. Okay, now incorporating these things, so W1 is 0.3 and W2 is 0.7. So we have Tg1 and Tg2. So if you substitute it, you will have to get what will be the glass transition temperature of the blend. And one more thing, if you look into this equation, you are able to figure out something else also, something different from the question I have made in the solution. What have I done?
Ma'am, you converted temperature to Kelvin.
Yes, perfect. I have converted temperature to Kelvin because this Fleury-Fox equation considers temperature in Kelvin. So whenever you're using any relation like these kind of equations, you have to, check what kind of units, that has been followed in that particular kind of equation. In certain cases, this is not important, but only thing you have to see is for unit consistency. But in certain cases, what is the unit used in that particular type of equation also plays a critical role in getting the correct answer, okay, the correct value. Okay, hope you got it. Now can you calculate and say what is the glass transition temperature? You have the equation, you have the values, you have to just substitute and say what it is.
$54.
For Kelvin or degree centigrade?
Degree centigrade.
Okay, degree Celsius, okay, okay. What about Paul? Are you also getting the same answer?
Ma'am, I'm doing.
You're doing okay, take your time.
Ma'am, I'm not getting.
Not getting. Okay. Let's see what is the answer. So 1 by Tg is equal to 0.3 by 223.16 plus 0.7 by 373.16. Okay. So the Tg of the blend you will get is 310.54 Kelvin, which is nothing but 37.4 degrees centigrade. Okay. You can just do the calculations and then recheck. Fine.
Okay, ma'am.
Yeah. Okay. Now let's proceed to the next question. So now match the range of interactions for the following type of non-bonded interactions. Okay. Uh, there are certain type of non-bonded interactions that are given. Okay. And the range of interaction, it's basically based on the distance between the molecule. I just request both of you to mute yourself, uh, so that we will not have this noise. Yeah, thank you. So when you're answering, you can just unmute and speak. Okay, otherwise we may get some interferences. Okay, to avoid that, just mute yourself when I'm speaking. Okay, so and then we have certain non-bonded interactions, and then we have the range of interaction. So the range is based on the distance between the molecules. Okay, which is nothing but r. So we have four types of non-bonded interactions. Okay, charge dipole, dispersion, charge interactions, and repulsive interaction. Now you have to tell me what is the relation for the range of interaction, whether it is for charge dipole, dispersion, charge, and repulsion. So whether it is 1 by r, 1 by r power 12, 1 by r square, 1 by r power 6, which matches with what? This is from the lecture interactions. It's just a direct question.
I didn't listen, ma'am. Maybe
Okay,
had to listen classes.
okay, fine. Paul, you want to make an attempt?
Yes, ma'am, I'll try.
Yeah, sure.
Uh, Repulsion is 1 by R raised to 12
Okay.
because that is the least.
Oh, okay.
Then charge to charge will be 1 by R raised to 6,
Hmm?
and dispersion would be 1 by R square,
Okay.
and charge dipole would be 1 by R.
Okay. Now let's see what is the answer. So charge dipole is actually 1 by r square. Dispersion is 1 by r power 6. Charge is 1 by r. Okay. And your repulsion is 1 by r raised to 12. Okay. So this is how the non-bonded interaction relates to the range of interaction. Fine. Uh, now
Okay,
let's
ma'am.
now let's proceed to the next question. Identify the crystallization model for the below statements. Okay, ratio of crystallinity as a function of time, and rate of crystallization based on cooling rate. Okay, so which one corresponds to what? So rate of crystallinity as a function of time and crystallization based on cooling rate. So does both of these statements corresponds to Abrami model, or A corresponds to Ozawa, B corresponds to Abrami, A corresponds to Abrami and B corresponds to Ozawa, or both A and B corresponds to Ozawa? So you have to tell me which corresponds to what. You both of you got the questions right? Any idea? You want to make an attempt?
Ma'am, I would tell Avrami model for A and Osawa model for B.
Okay. Okay. So, Avrami model, you're saying it, this statement one is for Avrami model. That is the ratio of crystallinity as a function of time. And Ozawa model is a crystallization based on cooling rates. Okay. So, Lakshman, you want to make an attempt?
No idea, ma'am. Actually, I didn't listen.
Okay. You said you didn't do. It's okay. Now let's see what is the answer. You're correct, Paul. So Avrami is ratio of crystallinity as a function of time, and Ozawa model is crystallization based on cooling rate. So Avrami is an isothermal crystallization model. Okay, and it is the ratio of crystallinity as a function of time. Okay, and here Ozawa model is a dynamic crystallization model. So dynamic model means what is happening? The crystallization is happening not at a single temperature but during the cooling process. So what happens during the cooling process? The temperature also changes and there's a time change also. Okay, that is why it's a dynamic process. Okay, and if the cooling rate is very fast, in both the cases, the exponent value, the second term value is going to be 1. Okay, here also it's going to be 1 and here also it's going to be 1. So 1 minus 1 you will end up in 0. That means no crystallinity. That means if there is a very fast cooling, rapid cooling as we discussed, you're going to end up in a sample which doesn't have any crystallinity. In other words, you're going to end up in a amorphous sample. Okay, hope both of you got it. Now let's go on to the next question. In polyvinylidene fluoride, orientation of crystal phase leads to what? Does it leads to disordering of amorphous phase, or does it lead to disordering of dipoles, or does it cause orientation of dipoles, or is it both A and C? What happens when there is a orientation of crystal phase? In case of PVDF.
Ma'am, I'm not sure, but I would go with option A,
You're saying disordering of amorphous phase, you're saying.
amorphous.
Option D.
You're saying option D, which is disordering of amorphous phase and orientation of dipoles.
Yes.
Okay. Why do you both feel that way?
I'm not sure, ma'am. Just guess.
Okay. It is actually orientation of dipoles. So the crystalline phase orientation, it actually also causes orientation of dipoles in case of PVDF. Okay. And it's nothing else related to amorphous phase. Okay. It's orientation of dipoles is what takes place when there's an orientation of crystal phase. Fine. Now next, identify the interactions at coarse grained level. So what are the interactions we take into consideration in a coarse grain modeling? Is it steric repulsion, or is it dipole-dipole interaction, or is it hydrodynamic interaction, excluded volume, or entanglement? So coarse grain level is nothing but some bulk molecular level, bulk level basically. Any idea?
I would tell
Steric
it is
repulsion.
entanglement.
No, one by one can you answer? 'Cause, 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 'cause One of you can start.
I,
Yeah.
I would tell it is entanglement.
Okay. Uh,
It's steric repulsion.
okay. So Paul is saying entanglement and Lakshman is saying steric repulsion. We'll see what is the actual answer. So both of you are right, and this has multiple answers. So steric repulsion also plays a role in coarse grain level analysis. Hydrodynamic interactions, okay, also plays a role, and finally the entanglement also. Okay, so these all play a role in coarse grain level interactions. Fine. Let's go to the next question. Polymer crystals shows a range of melting points in contrast to single melting points of crystals of small molecule. Why? It's a GATE 2021 question. Is it because there is an absence of intermolecular interaction, or is it because there is an absence of long range ordering, or the polymer chains are not in thermodynamic equilibrium in a metastable state, or the melting behavior of polymer crystal is independent of the sample thermal history? Why is it that there is a range of melting temperature uh, polymer crystal stores instead of a single melting point? What might be the possible reason?
Option C.
Okay, now they are not in thermodynamic equilibrium in a metastable state, you're saying. What about Paul? What is your opinion on this?
Ma'am, I would tell it's option A.
There is an absence of intermolecular interaction, you're saying. Okay, you both of you have told two different answers. Let's see what is the answer. It's actually option C, as you know, uh, Lakshman told. The polymer chains, they are not actually in a thermodynamic equilibrium in a metastable state. So that is a major reason that polymer crystal shows a range of melting points instead of a single melting point. Okay. Now let's go to the next question. Melt processing temperature of a semi-crystalline thermoplastic polymer is it between glass transition and melting temperature, or is it equal to the melting temperature, or is it lower than the melting temperature, or is it higher than the melting temperature? What is the melt processing temperature of a semi-crystalline thermoplastic polymer? At what temperature do we do a melt processing of semi-crystalline thermoplastic polymer?
Ma'am, I'm not sure, but I am telling option D, higher than melting temperature.
Okay,
You are singing equal to TM.
okay. Let's see what is the answer. It is actually option D, higher than the melting temperature. Okay, so higher than the melting temperature is what the system will be in a completely molten phase where the melt processing can be done. Okay, because in your equal to melting temperature there might be some solid phase left also. Okay, so higher than that, generally when you want uh, to be completely taken to a liquid phase, you just heat it to a temperature higher than the melting temperature, right? I hope you got it. Now let's proceed to the
Yes,
next
ma'am.
question. Viscosity measurements were performed for a set of PMMA solutions of different concentrations in Kelvin at 25 degrees centigrade. Okay, the plot of reduced viscosity against concentration of PMMA solutions produced an intercept of 21 centimeter cube per gram on the ordinate at C equal to 0. The value of viscosity average molecular weight of PMMA in toluene at 25 degrees centigrade is, what will be the viscosity average molecular weight? Additional information given is that the Markov constant K is 7.5 into 10 power minus 3 centimeter cube per gram, and A is 0.72 for PMMA in toluene at 25 degrees. So this is again a GATE 2020 question. So what are they given in the question and what are we supposed to find?
Ma'am, we should find MV bar.
Okay. MV bar is
I don't
nothing
know
but
how.
you don't know how to. Okay. See. Now let's see. So they have given something called Markov constants. Correct? So that means this is an hint. You can use something related to this Markov so that you will end up with the viscosity average molecular weight of PMMA. Alright? So what is that? We'll see. So the solution goes this way. So they have, as I said, Markov constant they have given. That means there is a equation called Markov's equation. So this equation is based on the intrinsic viscosity eta, which is given by the relation K into m per A, where m is your viscosity average molecular weight, K and A are the constants. Okay. So, and also we know the constant values, K and A values we know now. We have to find out what is m. So what information we have related to eta so that we can find m. What is the other information given in this question? There is one more information given in this question from which we can find out what is the intrinsic viscosity. What is that information? You can just read the question and say what is that additional information given which is going to help you in finding out eta.
Ma'am, we will use the plot of reduced viscosity.
Yes, yes, yes. We're going to use that. Okay. So now let's see how do we use that. So we have reduced viscosity against concentration, right? So this plot kind of thing will look like this. And they've given intercept. So the intercept and there is additional information, the intercept on ordinate. Ordinate is nothing but your y-axis at C equal to 0. C equal to 0 means concentration is 0, right? So this intercept is nothing but your intrinsic viscosity. So the plot of reduced viscosity versus concentration, the intercept of this plot will give you the intrinsic viscosity. It's nothing but reduced viscosity at concentration tending to 0. The intercept value is nothing but reduced viscosity at concentration tending to 0. So your reduced viscosity can also be expressed as eta Sp by C, which is eta Sp is nothing but your specific viscosity by C. So as C tends to 0, you get the y-intercept, which is nothing but your intrinsic viscosity. So what do we have? The y-intercept. We have the y-intercept value, which is 21 centimeter cube per gram. They have given this information also. So now we have all other parameters except for your viscosity average molecular weight. Correct? So we have what is eta, we have what is K, and what is A. Can you substitute and say what is M?
molar mass.
No, that is okay. That is viscosity average molecular weight. That is what this whole equation is about.
Okay. Okay,
I'm
ma'am.
saying what is the value? Calculate and say. That's what I'm saying.
Okay. Okay. Okay, ma'am.
Yeah. Both of you are trying. Are you both
Yes,
trying?
ma'am, I'm right.
Yeah, yeah. Okay, fine. Yeah, I'll wait for a few more minutes that you could calculate and see. Were you able to find out?
Ma'am, I am getting it as 61,336.
Okay.
Unusual.
Okay.
Seems like an unusual answer.
61,300 you're saying.
Yeah.
Why do you say it is unusual answer?
No, it's very high value.
Why do you think it's a very high value?
Oh, it's for a molecular weight. No, it's okay then. Molecular weight can be high.
It's a
Sorry,
molecular.
ma'am. I got confused.
Yeah, it's a molecular weight of a polymer.
Yeah.
Okay, so
Yeah.
it
Yeah.
can be of higher values. Okay, fine. Now let's see what is the answer. So we have eta is 21, K is 7.5 into 10 power minus 3 centimeter cube per gram, A is 0.72. Substituting it and then rearranging it, you get 61,336.57. I think you got this similar 61,300, right?
Yes, ma'am.
Yeah, you're right. Okay. Uh, Lakshman, you also got it. You're able to follow?
Yes, ma'am.
Okay, fine. Now let's proceed to the next question. Stretching of rubber leads to a decrease in alignment of polymer chain, increase in alignment of polymer chain, no change in alignment of polymer chain, or decrease in strength of rubber. What does it cause? When you stretch rubber, what happens? This is again a GATE 2013 question.
I would tell it's option B, increase in alignment,
Okay.
but I'm not sure though.
Okay. No worries. What about Lakshman?
A decrease in strength of rubber.
Hmm?
D, option D.
Saying decrease in strength of rubber. Okay. Now let's see what is the answer. It's actually increase in alignment of polymer chain. So when you start stretching the rubber, no, there starts alignment of molecules actually. So the alignment becomes much more uh, much higher compared to the initial alignment. Okay, the molecule starts aligning in the stretch direction, right? So there is an increase in alignment of polymer chains. So this is what is the answer. Okay. Now let's see what is next. Structures like helical, pleated macromolecules comes under vast structural level of biopolymers. Does it come under primary, secondary, tertiary, or quaternary? Helical structure, pleated structure. What kind of structural levels are these? Are these primaries, secondary, tertiary, or quaternary in case of biopolymers?
Tertiary.
Yes, secondary.
Secondary, one is saying secondary, one is saying tertiary. Okay. Uh, so let's see what's the answer. It is actually secondary. Okay, your primary basically deals with your linear branched chain and all those things. Secondary actually decides on the molecular interactions, okay, within the molecule, and because of that you will start forming in certain cases helical kind of structure or sheet kind of structure or pleated structures in case of biomolecules. Okay, and tertiary structure, it is mostly a interaction between two different chains. So you start ending up forming 3D structures. Okay, and then higher structural level is your quaternary structure. So secondary structure is what deals with the helical pleated structures of macromolecules. Okay, Lakshman, you got it.
Yes, ma'am.
Fine. Let's go on to the next question. Under the complexities of crystallization of polymers, identify the correctness of the below statement. Okay, so the actual melting temperature of a macromolecule is greater than the equilibrium melting temperature. Is it 2? Because so crystallization in polymers have a lot of complexities involved in it because of the polymer structure, the macromolecular nature. So we have to say whether it is true or false that the actual melting temperature is higher than the equilibrium melting temperature. Is this statement true or is it false?
True.
Saying. So both of you agree with it's true?
Yes, ma'am.
Okay. It's actually incorrect. Your actual melting temperature will be less than your equilibrium melting temperature in case of polymers. Okay. This is what is the relation. Okay. Uh, you can find from the relation that there are multiple parameters that are playing a role. So, for example, in this case, the Gibbs-Thomson equation, if you see, Tm is a function of Tm infinity, equilibrium melting temperature, multiplied by a factor which is 1 minus of different parameters like your surface energy, molar volume, heat of fusion, right? So, you will end up with a melting temperature which is lower than the equilibrium melting temperature. Okay, fine.
And
Got it?
can you repeat?
See, uh, when there is a melting temperature in case of polymers, there are a lot of parameters that comes into picture. Say for example, your surface energy of the crystal and melt phase. Okay, the molar volume of the repeating unit and the solvent. So all these things plays into picture, and what happens is that your actual melting temperature will be lower than uh, you know your equilibrium melting temperature. Okay, uh, fine, you got it. Because say for example your
No.
surface energy, it's going to play a role, so there will be some crystals left, right? So this crystals left will have its surface energy, and the surface energy, the energy tries to material tries to push itself to the liquid phase. Okay, because of the these kind of
Okay.
yeah.
Okay.
Hello.
Yes, ma'am.
Yeah, so it will start melting at much lower temperature than your equilibrium melting temperature. Okay.
Okay, ma'am.
Yeah,
Got it.
and also the interactions with the solvent and all these things plays important role. uh, okay.
Okay, ma'am.
Yeah, now let's go on to the next question. Anisotropy in refractive index due to orientation is referred to as, is it referred to as scattering, or is it birefringence, or is it poling, or is it stretching?
By reference.
Okay, both of you agree?
Scattering.
Scattering refractive index is actually birefringence, it's not scattering. Okay. In case of scattering, there is no change in the refractive index. Actually, it just starts. It's not able to move further. That it is, scattered in different directions or
Yes.
in specific directions. Okay.
Ma'am, can you explain once more the
No,
reason?
I didn't get you.
The reason, can you explain?
No, it's not scattering. I said because in scattering, it's when the light actually passes. Uh, if there is a scatterer, you know, what happens is that the light is not able to pass through that scatter the particle. Okay, it starts scattering in different directions. Okay, it does not pass through the material. Whereas in case of refractive index, the light actually when you are having some kind of a refractive index, that means the light is passing through the material, but due to the interaction of light with the material, in inside the material, the direction of the light is getting changed, and then it is coming out.
Okay. Okay, ma'am.
Okay, and in case of birefringence, actually what happens is that there is an anisotropy, that is at different points, it is not the same kind of refractive index you will have. There will be different refractive index, and this leads to the phenomena called as birefringence. Okay,
Okay, ma'am.
because yeah. Now next question. Identify the glass and rubbery region in the below figure. So you have a figure of volume versus temperature. Uh, you have this point as your glass transition temperature. So you have to identify which region is glassy and which region is rubbery. Whether between these two regions, this and this.
Temperature above glass transition is rubbery.
Okay. So you're saying this region is rubbery. and this region is glassy. So, Lakshman, do you agree?
Yes, ma'am.
Okay, both of you are right. It's temperature below glass transition, you will have a glassy region where the segmental mobility is arrested, and above glass transition, you have the rubbery region where you have a good segmental mobility. Okay, next. Melting phenomenon in a semicrystalline polymer is a dash order phase transition. Is it zeroth, first, second, or third?
First,
Yeah, first started.
Yeah, both of you are right. It's the first order. Okay, so there will be a discontinuity in the first derivative of your Gibbs free energy. Okay, uh, now next. So that's it with the question. Uh, we'll just see some of the questions posted in one of the earlier, sessions of this course during July November 2022. There were students who posted some questions in the forum, and those questions were answered by the uh, course instructor. We'll see what are those questions and what was the answer given. So the question for one is, why does natural rubber take more time for biodegradation even though it is from tree? Okay, this question was posted by a student called Nimalan. Okay, so the answer was natural rubber as extruded from tree will be easily biodegradable. It contains macromolecules, though they are not very high in molecular weight. Okay, but once we process it, what happens is that during processing, you start cross-linking, right? So cross-linking, you would have gone through in the lecture that in case of natural rubber, you do the vulcanization where you have the sulfur cross-linking, right? Are you able to remember or recollect? Vulcanization of rubber.
yes, ma'am.
This would be a very common, term you would have gone through in school also.
Yes, ma'am.
Yeah. So
Yes,
this
ma'am.
cross-linking actually makes the biodegradability difficult. Otherwise, if it is not cross-linked, as such, if you are taking from tree the natural rubber before processing, it is easily biodegradable. But once you process it and cross-link it, the degradation level reduces. Okay. There is one more question which was asked. So when the polymers are coiled, entangled, or random, and whether both coiled and entanglement is possible in a single polymeric system. There is a part B to the question also asked by the student. Is it theories such as ideal chain and expanded chain considered about polymer solution or polymer melt? And then third question he has asked is, all polymers including natural polymers such as jute, cellulose are viscoelastic. So he has asked multiple questions. So first question he has asked whether when do you have this coiled, entangled, and random structure, and whether both coiled and entanglement is possible in a single polymeric system. Second question what he has asked is ideal chain and expanded chain. When do we consider it? Whether we consider it in a solution state or in a polymer melt state. And third question he has asked is, are all polymers, including natural polymers, viscoelastic? So, what were the answers given? So, what is the answer is given is that coiled, random, rod-like, stretched are all with respect to single conformation of a single macromolecule. Okay, a single polymer molecule can have a random shape, coil shape, rod-like shape, stretched shape. Okay, whereas entanglement, it comes into picture when you have multiple macromolecules. Okay, for example, in a polymer melt, you will have multiple macromolecules. So when you have multiple macromolecules, or even in a polymer solution, very concentrated polymer solution, uh, you can have entanglements. but your entanglements comes more into picture when you have your polymer melts. So as such, you are ending up with multiple macromolecules, not a single molecule. Okay. So therefore, if the system is dilute, such as dilute polymer solution, then you can have coiled or stretched macromolecules and there will not be any entanglement. That means in a dilute polymer solution, you have very few molecules and there may not be that much of interactions so that the molecule starts entangling. On the other hand, if the system is concentrated, such as in polymer melt, then you can again have a coiled or stretched macromolecule. The individual molecule will be either coiled or stretched, but they will be entangled. Okay, since the concentration of macromolecules, the number of macromolecules are very high, they will be entangled. Okay, so this was the answer for the first question. The second question is theories such as ideal and expanded chain considered about polymer solution or melt. So these theories are applicable for solution, melt and also the rubbery state. So it is applicable for all these three conditions of solution, melt and rubbery state. Okay. So in all these states, there is sufficient thermal energy for conformation change to take place. And so you can observe the behavior of an ideal chain or an expanded chain as well. Okay. So in all this state, whether it is going to be a solution, polymer solution or polymer melt, or is it going to be a rubbery polymer, there is sufficient amount of the thermal energy for conformation of the macromolecule, conformation change of macromolecules to take place. So based on those conformational changes, you can end up with an ideal change or an expanded chain. Okay. And the final question, are all polymers viscoelastic, including natural polymers? Yes, they are viscoelastic. They do have both solid like as well as liquid like viscous as well as elastic behavior inherent in them. Okay. Hope you got some idea, some additional information. Are you both there?
Yes, ma'am.
Yes, ma'am.
Okay. So hope you got idea. So do you have any other doubts?
No, ma'am.
Okay. Uh, so there are no further doubts. So please go through the lecture. Okay. Go through the lecture. In case you have any doubts, please post it in the forum or you can also ask in the live session. So whatever possible I could answer, I will answer in that particular session, or else I'll try to answer it through the forum, or in the subsequent session I'll try to answer. Okay. Or if you're posting in the forum, we can, both myself and professor can answer through the forum. And also if some questions, if I'm not able to answer in the live session also, I can discuss with the professor and then get you back with the answer for those. Okay.
Yes, ma'am.
Yeah. uh, so if there are no other doubts, uh, we can officially end the session. Any other doubts?
No, ma'am.
Okay. Do you have any feedback on the session? Whether the content is fine, you're able to follow, this my speed is okay, or any modification to be changed in the content or my speed?
And ma'am, can you like include more numericals? They
You
are a
want
bit more challenging.
Okay, you want more numericals? Okay, sure. I'll try to add much more numericals. Fine, definitely. I'll try to add more numericals. Any other feedback? Any other feedback from Lakshman?
Yes, speed is fine, ma'am. Content is also good enough to.
Okay, but I request please go through the lectures before the session so that you can actively involve and uh, we can discuss it better. Okay.
Yes.
Yeah. So if there are no more questions, then we can officially end the session. Happy weekend. Thank you all.
Thank you, ma'am.
Thank you.
Thank you, ma'am.